So in this video we're going to look at a first order linear PDE, and we're going to use the change of variables approach. So we're not actually going to solve this thing all the way to the end, but we're going to look at the interesting bit, which is where we use the change of variables to convert the original PDE into a trivial one. So you can see the PDE here that we're looking at. We've got x squared du by dx plus y du by dy plus xyu equals 1. And this is what we want to turn into a trivial PDE. So the first step is to look at the characteristics, and so we need to look at the characteristic ordinary differential equation. So characteristic ODE, and in this case we can identify the coefficients A as x squared. That's whatever comes in front of the du by dx, that's x squared. And the second coefficient we're interested in is B, and that's what's ever in front of du by dy, so that's y in this case. So B equals y. And once we've worked out what those coefficients are, we can immediately write down our characteristic ordinary differential equation, which is dy by dx is b over a, so that's y divided by x squared here. And then we need to solve this ODE, which in this case is simple, because this is a separable first order ODE, and this is something we all know how to solve. So this is the integral dy over y equals the integral dx over x squared. So the solution is log y equals minus 1 over x plus some constant k. So that tells us what the characteristics, and if we know the characteristics, we know what to choose for one of our transformation variables. So this tells us that transform variable, so we were calling that eta, so that's equal to this constant, which is a function of it's a function of x and y, so that's log y plus 1 over x, which is constant along the characteristic. So that's one of our variables. Our other one, we have an arbitrary choice, or almost arbitrary choice. Arbitrary choice for the other. And we're going to choose that variable to be mu is just simply equal to x. So I say that's an arbitrary choice. It's arbitrary up to the extent that this transformation is non-singular, so let's check that. So let's check that our transform is okay. So check transform, and we do that by looking at the Jacobian, or the determinant of the Jacobian. So this is the determinant of the matrix d eta by dx, d mu by dx, d eta by dy, d mu by dy. So we have to go through and work out all of these derivatives now. So if I look at eta, so d eta by dx, I'm differentiating 1 over x. So this is minus x to the minus 2. If I then differentiate eta with respect to y, that gives me y minus 1. Then I look at mu. d mu by dx is 1, and d mu by dy is 0. Then I construct the the determinant. So I've got 0 times minus x to the minus 2 minus 1 times y to the minus 1. So this is minus 1 over y, which is non-zero. So this transformation is okay. So now we need to look at the derivatives. And use those to transform the PDE. Transform PDE. Okay, so du by dx is eta sub x du by d eta plus d mu by dx du by d mu. And we've already worked out derivatives in the Jacobian, so this is minus 1 over x squared du by d eta plus du by d mu, and for du by dy, so the same thing, d eta by dy du by d eta plus d mu by dy du by d mu, and here we just get one term, and this is 1 over y du by d eta. So these we take and we plug them into the PDE, and I'll just write that out again here so we've got it to look at. So my original PDE was x squared du by dx plus y du by dy plus x y u equals 1. So let's now plug in these new expressions for du by dx to start with. So this is minus 1 over x squared du by d eta plus du by d mu. Then we've got y times du by dy, and du by dy we're saying is 1 over y du by d eta. And I'm just going to leave this in terms of x and y for the moment and just worry about the derivatives to start off with. So what we can see is, if we look at these two terms, so if we look at this one first, I've got plus du by d eta, since the y's cancel. And if I look here, so the x squareds cancel, and that leaves me with minus du by d eta. So this first term and this term here cancel. So these cancel. And what that leaves me with is x squared du by d mu plus x y u equals 1. Okay, so we're nearly there. We've managed to eliminate one of our partial derivatives, but we've still got some x's and y's floating around, and really would like those also in terms of the new coordinates. So let's transform. So we need to transform x squared, and we also need to transform xy. So we know that, so by definition, x is equal to mu, and eta was given by log y plus 1 over x. So let's muck around with this second one. This gives me that log y equals eta, and then if x is equal to mu, this will be 1 minus 1 over mu. So therefore we can write y equals e to the eta minus 1 over mu. So now we know both x and y as explicit functions of the two new variables. So we can pop those into our PDE, which brings us to the end. So the trivial PDE solve is, so we've got x squared. Well, x squared is just going to be mu squared, du by d mu, and then we've got xy, so x is mu and y is e to the eta minus 1 over mu. That's multiplying u, and this is equal to 1. And that's the trivial PDE, which we should now solve if we want the general solution of the PDE that we started with. Now, we're not going to do that here. Let's just say that we could solve this. So could solve with an integrating factor. So that would be the exponential of the integral of 1 over mu e to the eta minus 1 over mu. But we're not going to do that basically because this is nasty. Okay, you can have a go, but it's kind of gross. Okay, so what we've done here is we've used the change of variable technique to go from a linear first order PDE, for which the solution wasn't obvious, to this trivial PDE, which at least in principle we can solve and get the general solution.